In this example, we will evaluate the integral of the square root of the quantity 5 plus 4x minus x squared. Now at first glance, this really appears to be a quite difficult integral. But the observation to make here is looking at what we have underneath the square root is if we can complete the square algebraically, then we'll hopefully be able to apply a trigonometric substitution. So before doing the trig sub, let's do a small bit of algebra. So what we have inside that square root is minus x squared plus 4x plus 5. And when we complete the square, it's ideal to have the leading coefficient, or the coefficient of x squared, to just be a 1. So I'm going to go ahead and just factor a minus out of everything. So x squared minus 4x minus 5. And if we go ahead and look at those first two terms, the x squared minus 4x, and we think what we would ideally have here is x minus some number squared. Well, the number that we would need to have squared to give us this middle coefficient of 4 is 2. So this would be x minus 2 squared. But recall, x minus 2 quantity squared, that's going to be x squared minus 4x plus 4. So if there's really a plus 4 coming along with what we have in parentheses here to balance it out with the minus 5, we need to think about putting a minus 4, and then there's the minus 5 which is there. And together this gives us minus the quantity x minus 2 squared minus the quantity minus 9. So plus 9. So rewriting our integrand, we have the antiderivative of the square root of 5 plus 4x minus x squared is equal to the antiderivative of the square root of 9 minus the quantity x minus 2 squared. And now we see something that we can apply a trig substitution to. So inside our integrand, we have this expression 9 minus something squared. So the trigonometric substitution we would like to use is take that x minus 2, or the something being squared, and set that equal to, in this case, a sine theta. The 9 squared is indicating that it should be 3 sine theta. That gives us x is equal to 2 plus 3 sine theta. So that dx is 3 cosine theta d theta. And what we've seen here is a common technique. If you have a random quadratic sitting underneath your square root, completing the square will allow us to apply a trigonometric substitution. So let's put this to work. So on the right here, I've kind of reminded us of the trigonometric substitution we're going to make, and we have the integral rewritten in this more convenient form. So this will become the antiderivative of the square root of 9 minus, and we're subtracting away from this the x minus 2 quantity squared. So that'd be 9 minus 9 sine squared theta, and the dx is 3 cosine theta d theta. And as we've hopefully kind of noticed here, the theme, we apply the trig substitution, then look for that corresponding identity. So what we have underneath the square root here is 9 times 1 minus sine squared theta. So when we take the square root of that, you're going to have a 3 which pulls out and combines with the 3 that we already have, so a 9. And 1 minus sine squared is the square root of cosine squared times cosine theta d theta, which is 9 integrals of cosine squared theta d theta. And at this point, hopefully anti-differentiating cosine squared and sine squared is really starting to feel like a routine calculation. So we rewrite the cosine squared in terms of the half angle formula, so there's a half that comes out front, Cosine squared is 1/2 times the quantity 1 plus cosine 2 theta. We anti-differentiate now term by term. So theta plus, 1/2 sine 2 theta plus c. And just like any of these trig substitutions applied to an indefinite integral, we get down to this final step and we have to resubstitute or somehow rewrite in terms of that original variable x. Now here I'm going to do a small intermediate step first just to make that task a bit easier for us. I'm going to recall the common trig identity. Sine 2 theta is 2 sine theta cosine theta. So the 2 times 1/2 cancel, and this is just sine theta cosine theta, all plus c. And now we can draw that associated right triangle. We know that x minus 2 over 3 is equal to sine of theta. So when we draw our right triangle, we have theta. So sine of theta is x minus 2 over 3. And using the Pythagorean theorem, we can label this bottom leg as 9 minus the quantity of x minus 2 squared underneath the square root. And this allows us to take care of our final step here. Theta, looking at the relationship between x and theta, will be the arc sine of x minus 2 over 3 plus sine of theta, which we know is x minus 2 over 3, times cosine theta, which looking at our right triangle should be adjacent over hypotenuse. So square root of 9 minus the quantity x minus 2 squared all over 3, and this is all plus c. Now just a few observations here. One, many of the integrals that we encounter will require multiple techniques of integration. So it is very reasonable to first have to do maybe a u substitution or here's some algebra like completing the square before getting to the trigonometric substitution. Additionally, let me also note that integrals typically require a bit more work and ingenuity than a derivative will require. So you do have to be persistent when you are attacking these integrals. Sometimes it will take a bunch of work. Other times you might go down a wrong path and then you have to kind of figure out what went wrong and maybe what a better approach might be. So that's a very important part of the learning process.